Alright, in this video we're going to examine the moment of inertia equations for a thin hoop. So this is our thin hoop here, a donut, and a solid cylinder. And we'll assume that in the case of the donut and the solid cylinder that where it is solid, the mass is uniformly distributed. And each of these objects is going to have the same mass and the same outer radius. Now one of the things that we find is different between these two things is the way that the radii are distributed. And I'm going to actually start with the middle one here. And what we see is that R1, which I'll call the inner radius, so R1 is, first of all, it's greater than 0. And the other thing about R1 is that it's less than R2. And that gives us this distinctive donut shape. So R1 is the closest that any mass is for the object, and R2 is the furthest that any mass is for this object. So if we apply those same definitions to this thin hoop, what we find is that R1 equals R2. Basically, all of our mass, the closest that any of the mass is also the furthest that any of the mass is. And if we look at this cylinder, we get something very different, which is that the closest that any of the mass is 0 distance away. And the furthest that it is of course greater than 0. It's all the way out here. And so what this means is that if we look at this, and we're trying to get as much mass, if we want our moment of inertia to be low, if we want this to be easy to turn, then we want more of our mass to start. We want our mass to start as close into the center as possible. And the further out that R1 goes, the harder it is going to be to get the same amount of mass in a cylinder type of shape to twist. And so what we get then is that if we look at this one, the moment of inertia equation is just mr squared. And if we look at this other case that we've dealt with for a little bit, it's 1/2 mr squared. And really where this is coming from, we can actually use the same equation for all of them, and I'll show you that with this one. Some of you looked this up and were a little bit confused about what this was trying to tell us. It actually looks like this, right? So we have 1/2 m and then the sum of the squares of the radii. What this is doing is it's biasing us towards larger numbers for the mass being further out. And I'll show you how this translates into the moments of inertia for each of these ones. So if I do 1/2 m times R1 squared plus R2 squared. Okay. What this winds up being then, though, is that R1 is equal to R2. So I end up with 1/2 m times 2r squared. Whoops. Sorry, the squared comes inside of there. It's 2 times r squared. Okay? And that gives me mr squared, which is exactly what we know the formula to be. And that's because all of our mass, the closest and the furthest our mass is the same distance away. And I can do a similar trick over here, where if I do 1/2 m r1 squared plus r2 squared, and r1 is 0, because that's the closest that any mass starts in, then we get 1/2 m r squared, where r represents r2 in this case. So we get, from the same basic formula, we can derive the moments of inertia equation for any of these types of shapes. And you can do this type of thing with a lot of them, although it can be quite tricky. But I'm just trying to show you the way that they all connect together. The other thing that I want to do is make sure that you understand how these moments of inertia then affect other quantities. So let's look at a question here of hardest to turn. So the first thing is we're going to look at hardest to twist. And if I call this 1, 2, and 3, if I were to rank these, it would be 1 is harder to twist than 2, which is harder to twist than 3. And this goes back to the idea of moment of inertia being equal to the torque over alpha. For any given alpha that you want, you're going to have to apply a larger torque given a larger moment of inertia. And I could rewrite that more like torque equals I times alpha. So if I want this to be a certain number, but this is bigger, I'm going to need a bigger torque. And torque is really how hard is it to twist? How hard are we trying to get this thing to twist? So in terms of hardness to twist, there we go. Let's ask a different question. Hardest to stop turning. So let's say it's already twisting. And there's two ways that this could go. One way that this could go is, let's say, given the same omega. So we've gotten these all turned so that they have the same angular velocity. And now we want to figure out which one's going to be the hardest to stop. So to do this, we could go one of two ways, actually. We could say, okay, let's look at it from the perspective of conservation or just angular momentum. So we could to change the angular momentum, you need a torque times the time. And what we should realize is that if it has a certain amount of omega, the change in angular momentum that we need, which is just going to be 0 minus I omega, because we're trying to stop it, so this would be our final, this would be our initial, equals torque times time. What this suggests to us is that for one having the largest moment of inertia, and all of them having the same omega, we're going to need a larger torque or a longer time for that torque to act. Another way to look at this is through energy. So we could just do work equals the change in kinetic energy, which will be 0 because we're going to try to stop it, minus 1/2 I omega squared. So this one, it's also pretty explicit. If we're saying that omega is the same in each case, then what we are going to need to do is more work. And this I could say is torque times theta equals the opposite of 1/2 I omega squared. So what we have to do then for our larger omega, for omega staying the same and a larger moment of inertia, we're going to have to either apply a larger torque or apply it for a greater distance. So these two are really telling us the same story. They're saying that if you have something with a larger moment of inertia, but it's rotating at the same speed, so if this is going around 5 times every second and this one's going around 5 times every second, good luck trying to stop this one. It's going to be much harder to get it to stop or change its motion than this one. Another type of question that we could ask would be actually looking at this one, and we could do something like given same energy. So let's say that we gave it the same amount of energy to start with. So we gave each of these an equal amount of energy. Well then, it depends on how you want to think about stopping it. If you want to stop it by using a torque over a distance, you'll find that regardless of the moment of inertia, if we gave them the same amount of energy to start with, they have the same amount of energy. We're going to need to take the same amount of energy away. So that means that we could apply the same amount of torque to each of these over the same angular distance, and they would stop. Now, what might be a little bit weird is that some of them then are going to behave a little bit differently in terms of the time that it takes if they have the same amount of energy. I'm not going to get into that too much because I feel like I really hammered that home when we were doing linear momentum and we did the elephant and the bullet slides. So you can go back to those if you want to see the relationship between time and distance. But because these are really equivalent, they're just rotational. But I did want to bring home the point that yes, it is harder to get this one to change its motion than it is to get this one to change its motion. And that's the same no matter what. But the way that we look at that could be very different. If I apply a constant torque, so if I do same torque, I get, and I want to rank the angular accelerations, it would be 3 is greater than 2 is greater than 1, right? So for the same amount of torque, I get different amounts of angular accelerations. On the other hand, if I do the same amount of angular velocity, so I just turn this one, and then I'm going to have to work harder, right, to get it to have the same omega as this one over here. But if I work harder and I get this up to the same omega, well, that means in order to stop it, I'm going to have to work harder to stop it as well. Okay, so we have to be careful about how we're viewing these things. Just because this is harder to get started, we need more torque, doesn't necessarily mean that it's always going to be the worst answer out there. If we give them the same amount of omega, this one definitely has more energy. It definitely has more angular momentum. It's definitely going to be harder to get this one to stop because moment of inertia means that it's harder to change the motion.